Good evening, everyone. Have you ever been approached by someone who was talking about nanotechnology and you didn't know what to respond? Well, if I believe Niels Boeing, who will have this talk now, you will after this session. Enjoy.
Okay. Okay, hi everybody. Thank you very much for coming. It's very nice to be here and tell you a bit what nanotechnology is. I think many people know a little bit. They know that's tiny, but then that's all. And probably the most important step in nanotechnology was the release of the iPod Nano, so that everybody knows, at least at the moment, oh, there is something like that. Just a word to on the picture you see there. It's a gold particle. It's you see the scale in the upper left corner. It's really very tiny. And what you see there is actually the atom layers. It's an electron microscope image. And well, you can do some nice things with this. But let's start then. So maybe the first occasion when somebody had the idea that you could do something like that with atoms was the physicist Richard Feynman. Maybe somebody knows him. He was a very important and creative physicist of the 20th century. And he said in 1959, in a lecture that was also between Christmas and New Year's Day at the Caltech, the principles of physics, as far as I can see, do not speak against the possibility of maneuvering things atom by atom. At this time, this was really a crazy idea because there were no tools, not even on the horizon, with which you could do that. So today, this speech, this lecture is regarded as the starting point of nanotechnology. But he didn't use the term. The term itself was coined in 1974 by a Japanese guy, Norio Taniguchi, and he just meant by it an extrapolation of microtechnology. He said, well, someday in the 80s we will move to the next smaller dimension. But then he never appeared again as a nanotechnologist, so it's a bit funny because he was never in nanotechnology really. Okay, what is this all about? This, the truth, well, it's kind of my private investigation on nanotechnology. Consists of 5 parts. The first one, of course, is what is it? What is nanotechnology? The second, what can already be done with it? Very important third one, what does not work yet? Because sometimes I think it's a bit difficult to see what's really fact and what is still fiction. Very important question, part 4, is how hazardous is nanotechnology? Because like all technologies, it's not just there and you can do nice things with it. And 5th is just, it's 2 short ideas how we could use nanotechnology for sustainable development, which is not the dominant perspective that people have. Mostly it's industry-driven and it's public-funded research, and what they, of course, have in mind is that they want to create new markets. So let's start with a definition. It's very important that you realize that it is not just another singular technology that deals with a certain object. Like, say, you have biotechnology dealing with all things that are happening within cells. I'd say it's more like a new phase of technology by itself. So the common definition is that nanotechnology means all processes or technical processes that deliberately create or use structures smaller than 100 nanometers, where quantum effects support new handling of matter. And this is just the culmination where different technologies that have been around for some decades merged together in the past, let's say, 15 years. So I think you have to have in mind this broad definition of nanotechnology to really understand what is so special about it. Otherwise, you could hear sometimes scientists arguing, Well, but this is only chemistry. We have been doing that for 50 years, so there's nothing new about it. That's not really true. A very important guy for the development of nanotechnology was Gerd Binnig, who invented the first real nanotool. I will show you that a bit later. And he says, at this moment, man is witnessing and shaping a second genesis, a fundamentally new evolution of material structures, which is a very poetic way to put it. But I think it is no exaggeration. Just to give you an idea what it means, a nanometer is a billionth of a meter or a millionth of a millimeter. And you see here in the left column some diameters of objects expressed in nanometers. So you see the diameter of the moon is 3.5 quadrillion nanometers. And then it goes down to the nanoscale, to the real nanoscale. The scale where we talk of nanotechnology is that what is shown in red. And there you see a lot of natural things, a virus, the ribosome, but also some artificial things like quantum dots or the nanotube. I think this is one of the most known things in nanotechnology. I will show you that a bit later. And then the smallest thing is the hydrogen atom, which is only 1/10 of a nanometer. Let's have a look at the ribosome. You could say this is a natural nanofactory. It's within everybody sitting down there in your cells, assembling the proteins from amino acids. Of course, this is a perspective that we have today. 100 years ago, nobody would have said of the ribosome that it's a kind of a factory, but from that you can see that through nanotechnology, the way in which we look at life is also changing. Life is now seen more like a kind of machinery, which has been approaching in the past 50 years. The diameter is 20 nanometers, so it's really quite small. And a bacterium has about 5,000 to 20,000 of these ribosomes in the cell, within itself. And they can assemble 10 amino acids per second, so that's already quite fast. And this is something that the nanotechnologists can't do yet. They would like to do that, but they have no idea how to build something as complex as a ribosome. But they have some tools already. So for our familiar way at looking tools, let's just group them together like sensing, grasping, and moving. They have particular kinds of microscopes. But you have to bear in mind that it's not an ordinary microscope. There's nothing really that you see there. All these pictures are generated by computers. They are translated from measurements. But then at the same time, sensing, grasping, and moving is all done with the same tool. For joining, you have the physical principle of self-organization and, of course, chemical bonds. Unfortunately, it's the only tool they have at the moment, and this is creating a few problems. Well, for cutting, although it's a bit funny to talk about cutting when you're already down there at atoms and molecules, because it's not really cutting with a knife or something like that, but just to take things apart, you have things like the ultraviolet lithography. Lithography is usually used to produce processors. But then if you want to produce really small features, let's say 10 nanometers, 20, you have to use light with a very short wavelength. And in EUV lithography, it's about 11 to 14, because the size of the feature that you can make with light, which is just like making a photograph, similar to that, is half of the wavelength. So if you use visible light, like let's say 400 nanometers, then you come down only to 200 nanometers feature size, which is not nanotechnology. It's just too big. So Gerd Binnig and Heinrich Rohrer, they worked at ABM in the late 70s. They invented the scanning tunneling microscope, and you could say it's like a Swiss knife of nanotechnology because you can do a lot of things with that. It took them 27 months to have the first measurement with this tool. And originally they wanted to do something completely different, as it is quite often in science. So it was more like a random discovery or random invention. But what they discovered is, if you look at the left picture, you see this tip. And you see at the end of the tip, there's only one atom left. And then you have a metal substrate, something that is electrically conductive. And if it's close enough, what happens is that you have one of the quantum effects I mentioned, that is a so-called tunneling current. That means by the laws of quantum mechanics, it can happen that an electron more or less jumps from the tip to the substrate, even if they are not in touch with each other. It's like in the macro world, you have nothing like that. You could compare it to somebody in a prison cell, that there is no probability that he will wake up the next morning outside of the cell, because there's the wall. He can't get through the wall. In quantum mechanics, there is a tiny probability that a particle jumps out of a cage. So that happens sometimes. And what they use is that from the intensity of this tunneling current, they can calculate the distance. And so the tip just follows the substrate surface, and then they keep the current at the same level, and then the whole tip goes up and down according to this current that they have fixed. And what you get by that is like a topographical map of atoms. You can really, you can not only make a 2D picture, you could do all that already with electron microscopes, but this time you can have like something, you can see the heights of the atoms, like this one that is a bit above the rest. And you can also use this one not only to make images of atom surfaces, you can also use this in the sense that that sometimes there is a chemical bond that arises between this one higher atom and the tip, and then you can just drag this atom across the surface. And maybe just for somebody who likes to do things himself, there's a website where there's a whole DIY manual how to build a scanning tunneling microscope for about €1,000 if you buy all these parts. Normally it's more like 10,000 up to 50,000 euro. So it's already a technology that could be used by anybody if he has €1,000, of course. This manipulation mode, what I told you, that you drag around atoms, that was discovered just by chance as well in 1989, and I think most of you will have seen these pictures because they are quite famous. They are like pictograms of nanotechnology. What you see in the lower picture on the left is IBM, because it was in an IBM laboratory in Almaden in California. And they were just playing around a little bit. They wanted just to take pictures of a platinum surface, and then they had xenon atoms on the surface. And then they just by chance discovered that they can move them. And so they started writing IBM with 35 xenon atoms on a platinum surface. Later, they made funny other pictures like this quantum corral on the right. That was more like a proof of principle, where you could see, okay, what Richard Feynman said in 1959, you can move atoms really. And before that, you couldn't do that. From the chemistry side, there are some processes you can use. The most important one is the so-called sol-gel process. That was already discovered in the late 1930s. by the glass manufacturer Schott in Jena. And you can do like thin films on glass or on any other surface. But then what they discovered in the 80s, if you take these small nanoparticles, you see the bigger things on the right-hand side. These are nanoparticles, just like, let's say, 10, 20 nanometers across. If you put some organic molecules on that, and then you go through the whole process, you can create these easy-to-clean surfaces. I think most of you know that, scratch-resistant, all that. That's already there. That's not a future application anymore. And you see in the upper picture, you see the soil, which is water molecules and the nanoparticles. And then you just remove the water, and then the nanoparticles start to form a network. And if you put this onto a surface as a very thin film that's maybe a few hundred nanometers thick, then by this physical principle of self-organizations, all these molecules that you have attached to the nanoparticles, then they will just stand up. It's like that you have a meadow of molecules, and these molecules all together, they create this effect that water doesn't stick to it or whatever. This is the whole secret behind these functional surfaces, as they are called. But another interesting thing that you can do with this self-organization, where structures are just created by themselves, you don't do really much with that. You just heat it up a bit or give that some thermodynamic conditions, and then you will create a structure. What you can do, was done the first time in the early 90s, that you can take small strands of DNA, which is in everybody's genome. And you know that's always two strands, they are like a ladder, which is like a helix twisted. But if you take just one of them, and then you look carefully at the order of these bases that you see, CA, CG, all that, then you can create other strands that have the complementary bases. And suddenly you form new structures that have not been there in nature. This is not a helix anymore. This cross is called Halliday junction. And then of course you can go on and create bigger scaffolds, bigger patterns like on the right side. And the idea behind is that maybe one day they could use this to assemble processors. They attach transistors to these DNA strands, and then they just put everything together, wait a bit, and it assembles by itself. Because if you think about moving all these tiny transistors with a scanning tunneling microscope, each separately, then I think it would take you 100,000 years or a million years. So this is like a first kind of nano building. This is really something new that had not been done before. Of course, they discovered some interesting particles. I think the two of them you already have seen somewhere, maybe in the media. This is carbon. Of course, these kinds of molecules have been around for millions of years, or in every campfire they are produced, just by chance, but nobody knew that they existed. Everybody knew there was diamond, there was graphite, and there was just plain carbon. And then in 1985, they first discovered the buckyball. This is the football on the right side, because it's exactly 60 atoms in the pattern of a football, which I like very much, because the actual football was introduced in '74 at the German championship, and 11 years later, they rediscovered it in the nanoscale. And the other one on the right side, this is the so-called nanotube, which is similar pattern from hexagons of carbon atoms, plus two half spheres at the ends. They can be very long, like micrometers, but they're only one nanometer in diameter. And the interesting thing about these nanotubes, they are like, let's say, they are a kind of superstar of nanomaterials, that they have a better electrical conductivity than copper, better thermal conductivity than diamond, they are stronger than steel. You can already put them together, spinning nanotube fibers out of them. You can make sheets, foils that resemble a little bit this stuff that you use in your refrigerator to keep things fresh. It's transparent, but if you put a voltage at the foil, at the sheet, then it starts glowing, emitting light or heat. And you can do some funny things with these nanotubes. But it's all not yet on an industrial scale. It's all like you could do that in principle. So this is more like, let's say, in the next 5 to 10 years, you will see something coming out of that. So second thing, what can you already do? Well, this is a lot of parts. It's 12 different applications. I don't want to mention all of them. But the most important thing about that is it's all materials. It's not yet nanosystems that you say you have complex structures, like the ribosome, for instance. That's kind of a machinery. It's only, you put some nanoparticles in metals, in plastic or whatever, and then you create a new property. And, well, you have these stain-repellent fabrics, that's 4 and 5 in textiles, that's already on the market. There are some companies, the most successful one is called nanotechs, like Gore-Tex, they knew how to name that. And then you have, let's say, 10 magnetic layers for compact data memory. That's in everybody's hard drive already, the giant magnetoresistance effect that was discovered in the 80s and was perfected for industrial production in the late 90s. So in every today's hard drives you have, in this sense, a nano component. So let's just show you a few applications, nanosensors. That's tiny structures that can react on single molecules, even single molecules. One very popular one is these cantilever arrays on the left side, where you put some molecules like biomolecules on, and if they attach together, then the cantilever is bent down. And this bending down you can read from a reflected laser beam, which is reflected differently if it's attached or not. So if the laser is reflected then differently, then you know, okay, there is something in the probe. Another thing is quantum dots. These are nanoparticles, let's say, like 5 to 20 nanometers in diameter, semiconductors. And they have a strange electronic structure. So what you can do is, if you attach, for instance, a DNA strand of anthrax in this hairpin mode on the left, and then you have one of these famous letters, and you put this stuff in, and if it's anthrax, then the complementary DNA strand attaches to this hairpin, the hairpin stretches out, and by this process the quantum dot is activated, so that when you shine light on this quantum dot, it will re-emit light and you will see a glow, and you can immediately say, well, that's anthrax. And that's already there, both of them. This is already products. It's not a concept anymore. Nanoelectronics, I mean, I don't have to tell you about the end of Moore's law and the problems of miniaturization in the next 10 years, maybe around 2015, when photolithography can't achieve that you have transistor features that are smaller than, let's say, 30, 40 nanometers. So there are a few different concepts. One is the millipede, which is developed so far that IBM could put it out as a product. They don't know if they want to do it already, because they don't know if there's a market or not. It's a bit like the early days of computing, that you have punch cards and you punch in with these cantilever tips small holes, and the holes represent the bits, and the diameter of one hole is 15 nanometers. So that means that even on the area of a coin, you could have, let's say, a few DVDs if it works. At the moment, the prototype is it's about 4,000 of these cantilevers. Of course, that's not enough. You would have more like millions of these cantilevers. The second is the crossbar ledge by Hewlett-Packard. That's more like a prototype. It's not as far as the millipede. This is a real molecular electronics concept, because you see these funny things in the middle. This is just a very big molecule. It's called rhodoxane. And this molecule can have two separate states. The ring can either be further down or further up. And then you could say, well, if it's up, it's a bit value 1, or if it's down, it's a bit value 0. And they have built already a prototype that is working quite well. But then, of course, nobody knows how many years it will take if we have like a crossbar ledge in a computer or for storage or whatever. Third thing is the nanotubes that I already mentioned. This is what you see, the blue line. This is a nanotube, and then you have a good comparison. These other big bars, these are the gold electrodes, and they have more the format of transistor features or electrode circuits on a processor as it is today. And then you can see the size difference. The only problem is this is only one nanotube transistor, so how do you integrate millions of them? And nobody knows this. And for that reason, they hope that they could do it, for instance, with these DNA scaffolds that I already showed you. Another interesting thing is are the nanosolar cells. It's a kind of artificial photosynthesis that was discovered in the 1980s by Michael Grätzel in Switzerland. And he discovered that if he puts together titanium dioxide nanoparticles and certain dye molecules, that the dye molecules, they harvest the sunlight, then they get excited, I mean in the electronic states, transfer energy to the nanoparticles, and these titanium dioxide particles are semiconductors as well, so the electrons are moved into the conduction band. And so this could create a current. And this already works. There are several companies out there who are, let's say, they are very near making a nanosolar cell product out of it. The efficiency is not as high as in conventional solar cells. It's only 10%, but you have to know that they absorb the whole range of daylight, all the different wavelengths, in contrast to what you have in traditional conventional solar cells. So if you look at this, then you could say they are already as good as the conventional ones. And the advantage is, of course, that it's very tiny, very flat. It's like 200 nanometers thick, this solar cell surface, or at the biggest 2 micrometers. And it could be flexible. They just put it onto a plastic film, and some even dream that you can paint your walls with a solar cell wall, and then you can harvest just sunlight energy. Would be very nice. Another thing is nanobiotechnology. This is a very crazy concept that works really well. That was discovered by a chemist, an American chemist, Angela Belcher. She now works at the MIT. What she did was she took a very simple virus, 880 nanometers long, and it's got only a few genes. You can see this ring on the right side. And one of the genes is responsible for the protein code that this virus has. So if they insert DNA strands just at random into the genes, then they cause a mutation. And what they want to get is a protein code that's attractive for semiconductor particles. So they just start with the first mutation that they make like gene technology, and then they put semiconductor nanoparticles into the petri dish where all the viruses are. And then some mutations express an affinity to semiconductors. So at some virus codes, protein codes, the semiconductors stick. They wash away all the rest, take only the ones that connected to the semiconductors. Then they make a second run of mutation, and so on. And they do it like an artificial evolution in 1 week. And at the end, you have a virus that has a genome that builds a protein code where all along, you see that on the right side, all along semiconductor nanoparticles get attracted. And what you want to do with that is construct nanowires for electronics. So this is maybe a new concept of exploiting nature, nature's nanotechnology, if you would like to say so, for creating something different like drugs, insulin. That has already been done 20 years ago. But Angela Belcher's aim is that one day she could create like circuits in a petri dish that are constructed by the viruses. Another thing is nanomedicine. This is a very big thing because there are already a few concepts that work quite nice. One is from Berlin that was developed here at the Charité. And what you do is you have super paramagnetic nanoparticles. This is just iron oxide. Coat them with some kinds of sugar molecules, and then you inject this into a tumor, brain tumor. That's where they started, because normally you won't get a drug through the blood-brain barrier if you just inject it into the bloodstream. And then because they are so tiny, they move into the cells. What you can see in the pictures are some cells, and the darker spots are these paramagnetic nanoparticles that have gathered in the cells. It's like in one cell, it's about 1 million, 100,000 to 1 million. And if you apply then an alternating magnetic field, these particles, because they are paramagnetic, they start vibrating. And this vibration, this is just motion, thermal motion, and that's heating up the tumor cells up to 70 degrees, but only very localized in the brain. It's not that the whole brain gets heated, it's really only the tumor. And so what they found in trials with, of course, mice at the beginning and rats and now even humans is that they have a very good rate that the tumors disappear and the people really get cured from brain tumors. What had not been possible or at this rate with, let's say, chemical therapies, something like that. And that will be probably in 2007 ready for application in hospitals. I have no idea how much it will cost, but so this is also more than only a proof of principle and a prototype. This is a concept that really works. But there are things that don't work. And these are the big dreams of nanotechnology, mostly. The other stuff that I showed you, you could say, well, this is very interesting and fascinating, but it's only one step more than what we already had. And what it is just create a macro object from millions of nano parts. Because, as I said with the transistor, nanotube transistor, it's very nice to have one in the laboratory that works, but then as you know that on processors today you have tens of millions of transistors, which are all created in the photolithography at the same time. You can't do that with nanotube transistors because you have no device, no tool to move 1 million nanotube transistors in the right position on the chip. And I think this is one very crucial step for the success, where you could say, well, this time we have really something new in nanotechnology that we did not have before, which has no precursor. The second thing is, which is highly debated has been since 1986, when this guy, Eric Drexler, introduced this in a book that was called Engines of Creation. And his idea was an assembly atom by atom with a device that he called an assembler. And the assembler got very popular in Michael Crichton's novel Prey. The problem with this concept is that all the parts that Drexler envisioned for this assembler, they only exist as computer models. There's nothing in reality. He published a big book in '92 called Nanosystems, where he had showed lots of simulations, chemical modeling, quantum mechanics, all that stuff. And these are two of the graphics that are in the book. What you see is a robotic arm that consists of 4 million atoms. It's about 100 nanometers high, and this tip, the working tip, that would, like in a factory, grasp an atom, put it there, and take the next atom, put it there, all that. And you would have millions and billions of these robotic arms. Another thing was that he said the transport of all the working material, molecules, particles, whatever, he would do that with these small wheels that you see, like a conveyor belt. The funny thing is, what he does is he takes the technology of the 19th century and just puts it down to the nanoscale. Well, why is it highly debated? Because, okay, some scientists don't like Drexler. They are very frank on that. They say he's an unpleasant guy. But apart from that, others say, well, all his ideas, they are not scientific. That doesn't work. The laws of physics don't allow that. But there's no consensus among the scientists if it's really impossible or not. So at the moment, we cannot say. And we cannot say if somebody someday will come up with this kind of assembler technology. It could be in 20 years, in 50, never, nobody knows. Meanwhile, because Drexler, there was a lot of criticism. The criticism was also because of the fact that all these tiny assemblers, which would act like, let's say, a swarm, like in Crichton's novel, could get out of control. And last year he reacted on that, and he abandoned his concept from '86, and he said, no, I think we can do it without assemblers. What he now sees is like a desktop factory where you have all these robotic arms just in a PC box, PC-sized box, somewhere at home. And of course, what you can't see is that these robotics arms on the left in the picture, they get smaller and smaller down to the nanoscale. So, but he doesn't know either how to do that. So it's all very theoretical. An interesting science fiction book about that was Neil Stephenson's Diamond Age. I think Neil Stephenson had more success with his Cryptonomicon. This is from 1995, and he just described a society where this molecular fabricator technology is already there. And you could go, if you're aware of some of the lower third or half of society and have not a lot of money or whatever, you could go to public meta compilers and get a sushi out or a blanket for the night because you have no home, something like that. One guy from the camp of Drexler, Robert Freitas, he introduced a concept in 1999, which is an artificial red blood cell. He calls it a respirocyte. And it's like 1 micrometer across. It consists of lots of pumps and energy stations, all that stuff. And what he says is, or what is the thinking behind these guys, is that the humans are so incomplete and so imperfect that we have to improve them. So get out all these natural red blood cells and get in the respirocytes, and then you can climb the Mount Everest without any extra oxygen. You could even sprint down 1 kilometer with the speed of a 100-meter race. It's all about efficiency for these guys. Okay, so far we have not touched very interesting subject, which is slowly coming up in the last 2 years. That is the question, well, are there any hazards? How hazardous is nanotechnology? The debate is hampered by the fact that the chemists say, well, we do only chemistry, ultrafine particles in diesel engines, that's nothing new. We have had that for 50 years, 60 years, so there is nothing new about nanotechnology. But when it gets to funding, getting money, of course, everybody says, well, nanotechnology is so revolutionary, so it's a bit difficult to see what's really happening there. So I propose we could look at it with regard to the potential ecological hazards, and let's say we have a classification like contained nanotechnology. There was the nanoelectronics or the microscopes, where the nano component is really fixed in the device, so nothing happens, probably. Nobody knows anything about recycling these things, but maybe that's a bit too early. The second is bioactive, and that's where it gets interesting, because you could have these small non-biological particles like nanotubes just free in the environment. Or what could be done with nanomedicine? Some weird ideas. The third disruptive would be Drexler's assemblers, that stuff, or artificial viruses. Artificial viruses, one has already been assembled 2 years ago by Craig Venter, who helped sequencing the human genome. And he put down a virus genome completely from scratch. This thing doesn't exist in nature. So even this is not completely out of reach. So if we look at the class, what I call class 2A, because class 1 is, I think, no big problem, the bioactive nanotechnology. What toxicologists have already shown is that these particles, they can move into the brain, liver, spleen, bone marrow, pass the blood-brain barrier because they are too small. They can enter into cells, and they can do some not so nice things in cells. For instance, they can cause oxidative stress. This is, you have a free electron, a radical somewhere, and this could, for instance, start a transcription of certain genes that should not be transcripted. And then something happens in your cells, and maybe you get an inflammation somewhere in the lung or whatever. And there are already a few studies where they have shown in the petri dish, but also in rats and mice, that there are problems, or in fish. For instance, the fish thing that was last year, that was got a lot of press, at least in the nano media. They put these buckyballs, the small footballs, into an aquarium, and 48 hours later, these fish had brain damage because they had the buckyballs in their brains. But this is only very preliminary. The question now is what to do about it. At the moment, there is nothing, no regulation for nanomaterials because, oh Jesus, I see that, but I think I get through it. The Royal Society, Royal Academy of Engineering last year published a very important and very interesting report, and they recommended that factories and research laboratories should treat manufactured nanoparticles as if they were hazardous. So they have to prove that they are innocent. The chemical industry, on the other hand, says, well, where's the problem? As long as they don't do damage, we don't need any regulation. So this is the debate now. Do you start regulating now? And do you ask from the chemical industry that they prove that it's not damaging? Or do you wait until shit happens and then you can start regulating? Yeah. And one of the experts says, well, that's his assessment. What is the state of toxicological information knowledge at the moment? He says it's only very limited. So no company can make any serious risk assessment with the toxicological, yeah, I see that, knowledge that they have at the moment. And they think that it's that we are 10 years away from a database or databases that could provide this knowledge. But in the meantime, of course, the development goes on. So class 2b, that is a bit more weird. This is that you could maybe turn the nanomedical ideas that I showed you with these, maybe not these paramagnetic particles for the brain tumor, but other concepts, that you could turn them into bioweapons, nanobioweapons, that are matched to certain genomes of parts of the population, because we know there are 3 million differences in the genome among humans, and you could exploit that. So that would be a completely new step in bioweapons. At the moment, none of this is part of the Bioweapons Convention or the Chemical Weapons Convention. So these two guys, Jürgen Altmann, Mark Gubro, they have been advocating for the past years that the possibility of nano weapons should be explicitly taken into the conventions. Well, but nothing happened, of course, it's just a proposal. Well, the disruptive nanotechnology, I mentioned already the artificial viruses or the nanoassemblers. What you have maybe heard is this worst case scenario of nanoassemblers, which is called gray goo. That is, the nanoassemblers get out of control. There are billions and trillions of them, and then they start just processing all the biomass they can find into copies of themselves. And then there's no way to stop that. This is highly debated, well, but it is a worst case scenario, and this guy, the nanomedicine guy, Robert Freitas, he made a calculation that if it starts at one point on the Earth with 10 meters per second, then it would take 23 days to convert all biomass on Earth into copies of these assemblers, which would cover then Earth like a gray goo, a machine goo. So this is what gets some people nightmares. And at the moment it's not yet clear. It's possible that in 5 years, maybe even in 3 years, we will have some kind of similar debate that we had in the early 90s about genetically manipulated organisms, GMO. The problem is that the nanotech guys, they say, well, we have to learn from that GMO disaster because it was a PR disaster for them. But then, at the other hand, they don't know how. There are no real proposals how to do that. They just, I have the impression that they just try to get through with it, and they hope nothing happens. But if you look at the beneficiary applications, then you could say energy. We had already the nano-solar cells. There are concepts for hydrogen storage for fuel cells made of nanoparticles. You could have better materials in cars, whatever, that will conserve energy in return. You could even provide clean drinking water with nanofilters that are already there, where you just put in sewage and you get clean water out. That works. And maybe a lot of other applications that I didn't think of. So you cannot say nanotechnology as a whole is potentially damaging or dangerous. You have really look closely of what part of nanotechnology you are talking. So this is the end. This is an idea I have. If we could not create a kind of open nanotechnology, open, one meaning transparent, that is, we have to get a public discourse started. We need the databases. If you look at the funding, just a number, the US, they put $220 million in military-related nanotechnology research, but only $3.5 million in risk research. So I think setting up comprehensive databases for nanotoxicology is a very urgent issue. The public discourse in Germany is mostly nothing. The UK is a bit further ahead. I think it's most interesting what's happening there. They had, this year they had the nano jury. There were just 20 citizens, ordinary citizens. They had no idea about that, like cab drivers and whatever. And they had sessions 5 weeks with experts, companies, scientists, and then they made up their mind a kind of recommendation to the British government where they should put the money in nanotech research. And they said, well, health, energy. So they had quite clear priorities. And I think we should start that in Germany too, but unfortunately at the ministry level there's nothing happening. But maybe Greenpeace will do it next year, I hope so, because this, in the UK, the nano jury was initiated by The Guardian and Greenpeace UK. The second idea is open could mean also open source, or let's say open design. Because like in every new technology nowadays, you have a patent rush. Also in nanotechnology, they start to create, to patent all I'm already done. They start to patent all kinds of molecules. If they just change something, some group of atoms, then boom, it's a patent. And we already know, and it's a topic at this Congress as well, that there's, for instance, this digital divide. I think if you look at how capital-intensive nanotechnology is, then it's very easy to foresee that in, let's say, 10 years, we will have a nano divide globally. So maybe we could start initiating like a kind of open material design domain. So no, this is just an idea that I have. I know that in open hardware there are approaches a bit similar to open source. Of course, hardware you can't copy by the million, but IBM, for instance, this year made open parts of the design of the new cell chip. There are some initiatives on the web that are creating open controller cards or whatever. There's even one initiative that's restarting again of an open source car. Maybe some people of you have heard about that. And that's where we have to get in. You, everybody. It's not just industry, it's not just markets. It's really, if we say it's a new phase of technology, then it's affecting all of us. So I think we should get involved, and if nobody wants us to be involved, then, well, we should say, please, we have a word. Okay, this is the book that I've written last year, where you can read, if you like, more about that, all a bit more detailed. There's also a website to the book. This is nanobitfaction.com. And, well, if there's something, just mail me. And, well, that's it.